Hi everyone. Today I wanted to talk about this encryption decryption problem I solved a couple of years ago, which had really intrigued me back then. And I find the solution quite innovative. And I will encourage all of you guys to also give it a try on your own. Not much prerequisite knowledge is really necessary for this. So it should be a good mind puzzle for everyone trying this problem. So as most encryption decryption problem goes, we have our two characters Bob and Alice. Now there's a safe that they want to break into, which has some passcode P. Now only Alice can go near the safe, whereas Bob will have to stay farther away. There are two numbers X and Y, but only Bob knows these two numbers. Now what happens is when Alice goes to the safe, this number P that she gets is either X or Y, and Alice has to say whether it is X or whether it is Y. Or rather, you can just visualize it as a simple yes no answer. So that means if p is equal to x, we say that yes. If p is equal to y, Alice says no. Once Alice actually goes here, Bob suddenly remembers which number is x, which number is y, but Alice does not know that. So what Bob can do is Bob can shout a number h to Alice, and based on that, Alice will have to make the prediction. Now, before actually going to open the safe, Bob and Alice can have some secret meetings. So, the idea is that they will basically decide on some encryption decryption method so that after Alice goes here and Bob suddenly remembers this X and Y values, Bob can say some number H to Alice, which will effectively help Alice recognize whether the number P given by the safe is X or Y. We also know from the problem that all these values are between 1 and 920. Notice that we have not fixed a bound on h yet. So h can be between 1 to some upper bound u. Now we will basically have to find the best possible solution for this u. Now let's just see an example to really clarify what I'm trying to say. Now for example, the x and y, these values are 56 and 101. Alice goes over to the safe. Bob suddenly remembers that X is 56 and Y is 101. Now, on Alice's side, if she sees 56, she should say yes. If she says 101, she should say no. And what about some other number? Well, by the constraints of the problem, we are guaranteed that this will never be possible. Now, notice that when Bob remembers this, he is allowed to again send this number H to Alice, and based on that, Alice can basically decide whether to say yes or whether to say no. Now, let me jump back to this constraint. Can we solve this with u equal to 20? That is, I can shout any number, or rather, not me, Bob can shout any number between 1 and 20 to Alice to help Alice make the decision. You can pause the video and try to think about a possible solution if you have. One hint would be try to look at the bitwise representations of the number. What can the solution be? Well, we can basically do this. Notice that 2 to the 10 is equal to 1024, which is greater than this 920 value, right? So using 10 bits, we can represent all the possible values of x, y, or p. Now the scheme 1 is like this. Bob has got x and y, and he wants to send a value h, using which Alice can recover the information as well. Or rather, given the particular p, he can say whether it is x or y. Well, the idea is just locate the first dissimilarity from the right, and based on whether x is 1 or x is 0 in that dissimilarity, we set a number. So there can be, of course, 10 possible choices, right? So I have numbered them from right to left. You can also number them from left to right. It doesn't really matter. So for example, here at the 0th occurrence, x and y are different, and x is 1 there. So we can say that h is 0, 0. The second digit is the position where they are different, and the first digit is 0 if x is 1, or 1 if x is 0. Or actually, just let's make this even simpler. Let's just say this is 1 0. The second position denotes the index, the first position denotes the character x is at that point, or rather the digit x is at that point. So here we have a discrepancy at the 0th index. Note that there are other discrepancies as well, but we are only considering the rightmost one. And 1, well, x is 1 here. So given this h, now Alice gets either x or y, right? So Alice just checks the 0th position. If it is a 1, that means she knows it's an x. If it's a 0, that means she knows it's a y. So she can answer the query correctly. Let's look at another example. Here, the 0th position is same for both, but the first position is different. So here, the position of discrepancy is 1. And what is x at this position? 0. So this is what Bob sends to Alice. So notice that the first digit can only be ever 0 or 1, and the second digit can be 0 to 9. So we vary from 0 all the way to 90. Now, if your bounds are 1 to 20, then just do a +1 every time you send h, and when you receive it at the Alice's end, you just do a -1. In this case, the upper bound on h is actually 20. Can we do better though? Well, I want to show a solution where u goes from 20 to actually just 12, which is like super cool for me at least, because even to represent all these numbers from 1 to 920, you need 10 bits and you have two of them, and you at least need to store some kind of this information where they are different and which is 1, which is 0. So we can do all that with just 2 additional bits of information. That is pretty awesome for me at least. So let's take a different kind of perspective. Instead of trying to pinpoint using our h itself where they're different, let's try to utilize the fact that they could meet earlier and decide on some other scheme. One thing they could have done is decide on some other representations of these x and y. Now, this may seem a bit silly or might seem to be the same thing, but the simplest representation is again just its bitwise representation. So, something like this. Now, I don't remember what 919 is or what 920 is in the bitwise form, but I hope you get the idea. Now, what we can try to do here, at least what my initial idea was that try to give a digit which is in one of the numbers and not in the second number. That way, only the positional information can correctly determine which number it is. So, for example, if we are taking something like, let's say, 5 and 6. Now, if they have already fixated on this particular representation, once Bob sees that, okay, 5 and 6 are the two possible numbers and I have to say some value of h over to Alice, then if 5 is x, then he can say, oh, h is equal to 0. Because at h is equal to 0, there is a 1 and there is a 0 for y. But what if x was equal to 6? Then he can say, oh, h is equal to 1. Because there is a 1 at the first position. So to make this clear, let me actually annotate this a bit. So this is actually the 0th position. This is actually the first position, the second position, and so on. So for h equal to 0, I just mean that at the 0th position, there is a 1. For h equal to 1, here at the first position, there is a 1. So something of that sort. And then the h value will automatically point towards the 1 digit in either of the number. So the strategy here is check which number, or rather I should not say which number, I should say check whether hth position is 1. If the hth position is 1, then that is our number, then we report yes. If the hth position is not 1, then we report no. Now the key question, does this work? Because I just took one example. Can you confirm whether this work overall or not? Well, to the keen viewer, you can kind of see this contradiction here. For example, 3 and 7. What if x equal to 3? Then you can either say this number or this number, right? You can either give h equal to 0 or h equal to 1. But for both of them, 7 is also having a 1 at both the places, right? So whatever value of h you give, Alice will not be able to know whether it's a 3 or a 7. Or rather, whether she should say yes or no. Because even if she got a 7, she would see that, oh, there's a 1 in both the places. So unfortunately, this particular representation does not work. But this seems like a promising idea, right? And I can say a little bit of a twist, which will make a similar idea work, but you have to think about how else to represent the number. And the hint here is that I said the upper bound I could reduce to 12, not 10. If this would work, then 10 would be the upper bound, right? But turns out 10 is probably not possible for this problem, but 12 certainly is. I hope you have thought about this a bit, but before I move on to the full solution, I should also say that for quite a while, I tried to figure out if there was something tricky with this number 920. Why such a weird number? Does 920 factorize in some way, or what? Like, why is this 920 here? Why not some other number? Well, turns out it was just a trick on the problem author's side. 920 does not have that much of a significance. So, that said, let's dive into the solution. The idea is we still want to represent numbers using some other form. Now, our main difficulty in the previous situation was when we had two different representations, but one of them was a subset of the other in some sense. So when I say subset, I'm just considering the elements which are 1. So here, for example, 3 was effectively a subset of 7 because every character of 3 which was a 1, it was also a 1 in 7. So we could have said some digit in 7 which was not in 3, but not the other way around. And there are other examples as well, like just take 2 and 3. We run into the same kind of problems. How to make bitwise representations without one of them being the subset of the other? Well, first things first, can you use such a representation with less than 10 bits? Not really, because you have to cover 1 to 920, and if you only have 9 bits, then you can only cover till 512. So you need at least 10 bits, and probably more, because this is a pretty good 10-bit representation. So probably we need more. Now the second question, how do we prevent overlaps? Well, one way to solve it is if we fix the number of 1 digits in the representation. If every representation has exactly, let's say, k number of 1s, then one of them could not entirely overlap the other without both of them being the same, right? So there could not be like 1 1 1 1 and 1 1 1 1 1 because the number of k is different. Like there is 5 here, there is 4 here, but we want all of them to have exactly k number of 1s. Now if you want them to have exactly the same positions of 1, they have to be the same number effectively. Notice that I have omitted the 0, but hopefully you get the idea. So for example, here I have set k equal to 5, but we can also try with some other values of k. Now the solution here is that you choose 12 total bits, and then for every number you choose a different set of 6 bits to be turned on. So how many such total numbers can be found? Well, 12c6, which turns out to be 924. So it turns out that 920 was actually not the important number, 924 was. Now, just to clarify, let's get back to how we are actually going to make these representations. So for example, 1 could be represented as 0, 0, 0, 0, 0, 0, and then 1, 1, 1, 1. 2 can be represented as 0, 0, 0, 0, 0, 1, 0, 1, 1. 3 can be represented as 1, 0, 1, 1, 0, or like something of that sort, which has basically 12 bits and 6 of them are turned on. So 3, 4, 7, 8, 9, 10, 11, 12. Point being, for any x and y, the bitwise representations will never be a subset of the other, because there are exactly k of them set to 1, and you cannot have an overlapping subset property if x not equal to y. Now, obviously, uh, if x and y are different, we want them to be represented by different bitwise patterns or different representation. Hopefully, that is obvious. Now, 12c6, this seems to be a somewhat of a magic number, and this is basically the upper bound, right? This is just the number of things we are setting to 1. This is the number of bits, or rather, not the number of bits, but we will basically be using from 1 to 12 as h to basically signify which of the bit is different, and we will choose a bit in x which is 1 in x and 0 in y. So for example, if x equal to 2 and y equal to 3, we will choose, let's say, this bit, because this is 1 here and 0 in y, and this will have some number from, let's say, left to right. We just number them left to right. This bit will have some number, and that will be the value of h. Now that number can only be between 1 and 12, right? Because there are only 12 bits. So notice that the value of h will only be from 1 to 12, but each of Alice and Bob now memorizes all these representations for each of the numbers 1 to 920. We did not have any restriction on what they could memorize. We just had a restriction on the information that could be passed from Bob to Alice at the last moment. Now, can we make this 11? Well, turns out no. You cannot have anything like 11, let's say 11 choose 4 or 11 choose 5. This basically means that you have 11 total bits, and out of them, 4 of them you want to be white, or rather 1. Now, smaller numbers like 11c4, 11c5, these do not work, because you cannot represent 1 to 920 with 11c4. I mean, just because both of these numbers are less than 920. So if you have 11 bits and you choose that only 4 of them will be 1, the number of possible ways to do that is lesser than the number of numbers we have to represent. So it turns out that 12 is the smallest number for which there exists some number of ones that we need to turn on. So for example, in this case it is 6, so that the number of possible such combinations is greater than 920. So just to conclude, what we basically do is for each of 1, 2, 3 and so on till 920, we assign them a specific bitwise representation consisting of exactly 12 bits, out of which exactly 6 are 1. So for example, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0. And the total number of such possibilities is 12c6. this, which comes out to be 924. Now between any two numbers, there will be, so for example, let's just say this is the other representation. There will be at least one distinct digit here and one distinct digit here, or rather one place here, one place here, such that it is 1 on this number and 0 on this number, and similarly this is 1 on this number, 0 on this number. So given x and y, we can basically choose the place where x has a 1 here and y has a 0 here for any given x and y, and then that number h will be less than 12, right? Because there are 12 bits, so 12 possible places. This number will be shouted to by Bob to Alice, and Alice will basically just check whether the hth position of the number p that she gets is 1 or 0. If it is 1, then that is the actual x, so she will basically say yes. If the place is 0, if the hth place is 0, then she will say no. So this was the final solution for the problem. If you can improve the solution or find a better way to encrypt and decrypt this message, then feel free to write in the comments. Or if you have some other ideas for upper bounds which are not 12 but between 12 to 20, and there are such ideas, so if you find them, feel free to discuss in the comments as well. Formally, this problem came in the Central European Olympiad in Informatics 2014 day 1 by the problem name questions. Feel free to check that out as well. I will attach a link in the description for this. Thank you all for seeing this video.